All right, lesson 6B, function model validation again. So it says we want to observe both of the residual plot and the endpoint behavior when choosing an appropriate model. Remember, if the residual plot follows a regular pattern, then there is behavior that is not accounted for by the kind of function that's chosen. So if you see any type of pattern in your residual plot, you probably ran the wrong regression. All right, if the residual plot has no identifiable pattern, then the regression equation most likely will model all but random fluctuations in the data. All right, so example 7 says your biology teacher has bacterial cultures for a class of 24 students. Each student is measuring the number of bacteria, Y, in his or her culture at intervals of time, X hours during the day. The results are shown in the table and the scatter plot below. A says find a power function regression model and the coefficient of determination R squared. All right, so make sure your data is all in your calculator, and then we're going to go and run regression. But remember, to get that R squared turned on, you're going to have to go to, we found a shortcut actually in class. So if you will go to mode, look down it, and there's a thing that says stat diagnostic, and turn it on. Okay, you'll go to mode, go down until you see stat diagnostic. I don't know why I did that. I was thinking on, but so I misspelled it. All right, and then turn that on right there. You don't have to do the second 0. Or remember, second 0, D, scroll down to diagnostic on and hit enter to choose it and enter till it says done. But if you turn it on in the mode, it'll be right there. All right, so if you need to pause the video, put your data in your calculator. Remember, your X's are going to go in L1, and notice there are 2 rows of X's, so just continue it. And then your Y's are going to go into L2, same thing, so just continue it. All right, so I put all my data in my calculator, and so I ran my power function regression. So I went to stat calc, and I went and found where it says power regression, and it gave me the equation. So my Y hat equals 291.964 x raised to the 1.221. And it told me that my R squared is equal to 0.9505, which is a pretty good fit. So R squared is close to 1. We think it's a pretty good fit. I did go ahead when I did this, I also pasted it into my Y1. So if I need to look at the graph, which I will in a few minutes, it's already there for me. If you didn't do it, you can go ahead and run that regression again real quick and paste it into your Y1, or you can do it later. It's up to you. All right, B says find an exponential regression model and the coefficient of determination. So we're going to find the exponential regression model. So we're going to go back into our stat calc, and we're going to go find exponential regression. And let's go write down that equation. So we get Y hat equals 180.658 times 1.699 raised to the X. And it has an R squared value of 0.968, which is a really good value as well. It's actually a little bit better than the power function, but we're going to look at them together in just a minute here and see why, which one is better, and why we think the exponential function is a little bit higher. All right, so on C. Oops, wrong button. All right, C says discuss the right end point behavior and the left end point behavior in relation to the regression equations. Which model better represents the data set and why? All right, so if you will go and turn on your stat plot, we're just going to look at the data. So make sure that your X list is your L1s and your Y list is your L2, okay? We're not doing the residual plot, we're doing the data plot. All right, so when you go in here and look at it, you'll see your power regression, something like this, and you'll see your exponential regression that looks something like this, okay? If we look at the middle here, in the middle, it could go either way, okay? Our data kind of fits both of them. It's kind of in between either way. But let's look at the left hand and the right hand side. Look at this. Notice that power regression is going to continue to kind of go down, where my exponential is curving, and how if we look just right here, we can see our data is curving as well. So that's one reason that exponential is just a little bit higher on the r squared value. If you look at on the other side of it there, if you look at the right-hand side behavior, again, notice that my data appears to be going up more like the exponential, where that power regression is still kind of going down below it a little bit, okay? So the end behavior fits better with the exponential. So not just the middle where both of them were pretty good, but also the end behavior. So which model would better represent the data set? That's going to be our exponential function. So the exponential function better fits the data set. As it curves on the left and right hand side along with the data. Now, just with the data they gave us, it doesn't mean the power regression is a bad function, just means the exponential is better, okay? Then D says, using the exponential model, find the number of bacteria in the initial sample. So remember, the initial sample is at our time 0. So I'm kind of just putting in function notation here. So I'm plugging in 0, but I still left it as the y hat. All right, so it's going to be that 180.658 times 1.699 raised to the 0. Or remember, the initial value is always our A value. Okay, so either way we get this, we end up with 180.658, which would be approximately 181 bacteria. And then it says to make a prediction for the number of bacteria present at 24 hours. Oops. All right, so now we're just going to plug in the 24 for our x value. All right, or we could go, we have our equation in y2. Okay, so hopefully I didn't say it when we were talking about it, I think. But anytime I run the regression, I save it. And since I saved that power regression in my y1, I saved the exponential in my y2. And so if I wanted to, I could just go to my table and look, okay? So if I go to my table and look, which is the number I wrote down in my notes here, so that's why I'm talking about it. I go to where x is 24, and I can see that it is 60,790,166 point something. So I'm going to say 67 bacteria. Now, if you just plug the equation into your calculator, you're going to get 60,400,000 and something thousand. Okay, so it's going to be off a little bit, but if you use the equation, it's rounded. That 0.658 was rounded. The 0.699 there is rounded, okay? So the 60 million is closer to the actual value. And then E wants to know, when will the number of bacteria reach 10,000? So this is where we're going to, number of bacteria are y's, so this is where 10,000 is equal to our equation. And we're looking for x. Okay, so again, this could be our y1, y2 intersect. But let's think about it, because we put stuff in y1 and y2. And y1 was our power function. We really don't need it for anything else, so I could erase it. I could clear y1 and put 10,000 in there. If you don't want to clear y1 because you're like, I might need it for the next part or something, then just go turn the equation off. Remember, put your cursor on top of the equal sign and hit enter. It'll turn that equation off, and that way your calculator doesn't even see it as anything is there, but it's still there. So if you're going to do that, then you would put this second part into y3, okay? You already have the equation in y2, so that part's good. And either put the 10,000 in y1 or put the 10,000 in y3 and make sure y1 is turned off. So then go to second, trace intersect, and enter. And so it's going to tell you that the X value is approximately 7.570, and this is hours. All right, example 8. While driving down a dirt road, you punctured the tire of your truck. The table below shows the pressure Y measured in pounds per square inch, PSI, if the air in the tire at any given time, X, measured in seconds after the tire was punctured. So put your data in your calculator, and then let's go answer the questions. So A says find an exponential function in the form of Y equals A times B to the X that best fits the data. What is the coefficient of determination? All right, so what is our R squared? So we're going to go put your data in your calculator, and then you're going to run regression. We want exponential. Oops, sorry, didn't have my pen turned on. Touched my screen. All right, and so we should get the equation. Our Y hat, our predicted value is equal to 33.880 times 0.955 raised to the X. And I have an R squared value of 0.989. Now, if you cleared your calculator, remember, go back and turn that diagnostic on. All right, B wants us to plot the equation and the scatter plot on the same screen. Does the exponential function fit the data points, and explain? So when I graph this, here's my data points, and here's my equation. It is pretty much on it, right? So it says, does the exponential function fit the data points? Yes, the data points are very close to the curve of the regression line. Regression, I'm going to put equation instead of line. C says using the model, what was the pressure of the tire before it was punctured? Remember, your X is the time in seconds after the tire was punctured, so it's asking you what was the initial tire pressure, so that's at time 0. Okay, or we know that that is that A value, the initial. So we get 33.880 PSI. All right, and D says the residual graph is shown at the right. Does this match your calculation? So you can go in and look at your residual plot. Make sure you can see the positives and the negatives of it, okay? And it should look like this. Says, does this match your calculation? So yes, it does. And what does it tell you about the validity of your regression equation? Well, we have some that are positive, some that are negative. They're really close to that x-axis there. So that means that the errors are close to the regression line, or points are close to the regression line. So, and I don't see any type of really pattern going on too much here. It's kind of above and on and below and up and down. And so this one is, there's no identifiable pattern. I can't spell, I apologize. Identifiable pattern. So this is a good model for the data. All right, example 9 says a data set has an upward trend shown in the plot below. It is not clear whether the best fitting function is linear or exponential. Use the residual plots to determine which regression function would best model the data set and explain why. All right, so they gave us this first one here is our data plot, okay? So when I look at it, I can see where they think it might be linear. Maybe down just a little bit from that. And I can also see where they think it might be exponential. Okay, so they ran both of the regressions. They looked at both of the residual plots. Okay, and so which one appears to be more random? I kind of see something happening with the linear. The exponential, it's just kind of all over the place. There's one below, one above, one below, one above, one below, one above, one below, three above, and then one below the x-axis. But here I kind of see where like these two are kind of together. These are all kind of below, and then over here we're above. So we've got, it's not a true quadratic shape, but they're kind of a little bit in a pattern of a quadratic there, okay? I mean, it's not as nice as if they'd have given us a pattern like this. But we kind of see it matches. There's a little bit of a pattern going on there, where the exponential function, we don't really have a pattern. Also, the exponential functions, almost all of the data points are closer to that x-axis, so it's a little bit better of a fit there. Okay, but these both might have been things that when they ran the regression, their r-squared values were super close. Which one's better? Well, the one that we don't see any pattern with, okay? So for the linear function, there is a slight pattern. And so we think the exponential function has no identifiable pattern. And is the better model for this data. All right, example 10. Textbook publisher prints textbooks X in thousands of units at a cost in thousands of dollars. The following data set represents the weekly cost C. A says find the average rate of change in cost from 10,000 to 13,000. Well, remember, average rate of change is just the slope between 2 points of a nonlinear function, or what's usually nonlinear. So we're going to go find that average rate of change. Between 10,000 and 13,000 textbooks. Well, remember, the X's and the Y's, or the X's and the C's here, are both in thousands of units, or whatever they are, okay? So we're looking between 10 and 13 right here. So I'm going to do my Y's. Find the difference in my Y's over the difference in my X's. All right, since they're both in thousands of dollars, that's why I did 13 minus 10, not 13,000 minus 10,000, because the books were in thousands of units, so they were also, really it was 167.5 thousand and 153,000. So I just took the thousands out of both of them. And so I do this, divide it out, and I get $4.833 thousand per book. So $1,000 per book. All right, find the average rate of change in cost from 18,000 to 20,000. So same thing, but now I'm looking at these two. This can be the 187.7 minus 182.5 over 20 minus 18. So subtract them, divide it, and I found $2.6 thousand per book. And then C says find a cubic regression model for the data set. So make sure this is in your stat edit, and we're going to go run cubic regression. All right, so my cubic regression, it said cost was our Y, so that's why I put C hat, is equal to 0.019 cubed minus 0.896 squared plus 15.519 plus 75.147. All right, D, ask about R squared. What is the coefficient of determination? And what does this tell you? So our R squared was equal to 0.942. And so that is close to 1. So this model, or this regression model, is a good fit for this data. E says, does the residual graph indicate this is an effective model, and explain? So we're going to go to your stat plot, make sure your X's are L1s, your X list is L1s, your Y list is going to be those residuals. Go look at that plot and look and see, are they random? It is random, and notice your points are going to be close to that X axis. So yes, the residual plot is random. And the points are close to the x-axis. All right, what is the cost of the publisher if no books are printed? So this is when X is 0. So we just plug 0 into our equation. It is our initial value. Now this is a cubic function, so remember it's your constant value in the equation. So it's at 75.147 blah blah blah. So it's going to be $75.15. Maybe remember, I'm sorry, this is in thousands. So it's $75.15 thousand. All right, use your cubic regression model to predict the cost to print 24,000 textbooks per week. All right, so I plug 24 into my equation, or I'm going to go check my table when X is 24, so I find it's $194.70 thousand. All right, evaluating a model for improved performance. So data analysis might have different business implications. There are instances where a business might want to overestimate in order to provide a service or product, or underestimate in order to keep costs in line. So example 11, says the demand for motorized scooters in a large city center is shown in the table below. For the 30 days in the study, each day's scooter demand is given in the calendar below. For example, on day 1, there was a demand of 35 scooters. So what is showing this there on day 1, the demand is 35 scooters when the temperature is around 65 degrees, okay? So the demand for these scooters is going to depend on the temperature. So you're going to take and put your temperatures in your L1, those are your X's, and the Y's are going to be the demand of the scooters, okay? So L1 for your temperature and L2 for the number of scooters. So these are almost like ordered pairs, but instead of being written as an ordered pair, it's got a slash in between it. All right, so go create your table. And then we're going to start running some regression and see which one seems to fit the best. When you go to run your regression, it doesn't tell us which one. It just says find the best regression equation model and the R squared value for the data set and explain your reasoning, okay? So go through, run your regression, go look at your data plot, okay? So go turn on that stat plot and make sure it's L1s or your X list and L2s or your Y list. And look and see, what does it kind of look like? So to me, it's like, oh, it kind of looks like it could be exponential. It could be quadratic. or it could be possibly a power function from the way that it looked, okay? So go through and run each of those and compare those R-squared values and see which one seems to work better. All right, so I went through and did that, and so I believe that the best regression equation for it was the exponential one. All right, so we got our y hat is equal to 2.487 times 1.041 raised to the x, but its r squared was only a 0.513. Not really high, but we'll talk about that, okay? The city wants to remove the outliers in the data for scooter demand on any given day. What 5 outliers would you remove? Use the residual values to justify your choices. So I'm looking at the residual values that have the larger error. They are further away from that x-axis, okay? And there's 5 of them there, so we need to go find them. And so we can use the trace feature to be able to do it. And so just randomly going through, finding the ones that kind of look the feathers, or to be honest, you could even go to your L3 and put your residuals in it and go find those residuals that are the furthest away from 0. Whether they're positive or negative, that's really the best way to do it, because it was really hard for me to tell on that stat plot. So I went to L3, put those residuals, so go up on L3, go to second stat residuals, and hit enter, and let it give you your residuals. You're looking for the ones that are the furthest from 0. All right, so I went through and I found the 5 that were furthest from 0. One of them was at 75 and 83. Another one was at 84 and 137. 85 and 164. 62, 67. And 80 and 300. I can't read my own handwriting here. Oh, not 300. 80 and 35. Okay, so those are the ones that were furthest away, and it wants to know that residual error. So I also wrote down the value that went with it. So the residual for the 75 and 83 was 32.872. The next one was 65.118. 89.181. 37.217. And negative 26.242. Then it tells us to remove these outliers and recalculate the regression equation. Did this improve our r-squared value? So go in there and delete those points. So in L1, delete 75 and go straight over to L2 and delete the 83. Literally get on those numbers, find that ordered pair, and delete it. Then 84 and 137, 85 and 164, and then the other 2 points as well. Then we're going to run our regression again. So let's go ahead and run our exponential regression. So when I reran it then, I get my expected value to be 4.045 times 1.032 raised to the x. And my r-squared value is now 0.626. So did it improve the r-squared value? So yes, r-squared improved. Still not great, but it's closer to 1 than what it was. And then it says, what other type of analysis could the city explore to better understand the demand for scooters? So we know the demand isn't just for weather, okay? So what other things could cause that? Yes, weather can. So I'm going to go ahead and write that. So weather as far as is it cold versus warm? We know the warmer it's going to be, the more scooters are going to be used, cold, until you get extremely hot, right? We also have, if it's raining, okay, that will affect it as well. People don't want to ride the scooters if it's raining. Events going on. All right, so maybe they have some big weekend event, okay? Maybe we're in Louisiana and we're talking about Mardi Gras or something like that, okay? So think about the events that are occurring. Also, if there are any conferences or meetings going on, the more people that are going to be around, the more likely the scooters are going to be rented, unless, of course, it's raining or it's too cold or it's overly hot. All right, so there's probably more. Those are just the ones that I came up with. All right, and that is the end of lesson 6.